In this video, Periodicity Part 1, we're going to cover the forces that affect periodicity and the periodicity of ionization energy, electron affinity, and electronegativity. First, definitions. Ionization energy is the energy needed to remove the outermost electron from a gaseous atom. So if we have the sodium atom, which has this electron configuration, and we remove one electron from it, now it's going to lose its 3s1 electron. That will give it the electron configuration of the closest noble gas, which is neon with 10 electrons, and that is a low energy stable electron configuration. Note the position of sodium on the periodic table and the position of neon. Neon is the noble gas in the period before sodium. So sodium, which is atomic number 11, loses one electron. It'll have 10 electrons, just like neon, and will become low energy and stable. So ionization energy, the energy needed to remove, which forms positive ions because of the loss of the negative electrons. Electron affinity is the energy change associated with the addition of an electron to a gaseous atom. Here we have chlorine in the gaseous state and chlorine's electron configuration. Now we're going to add an electron to it, and so the 3p5 is going to turn into the 3p6, and chlorine now will have 18 electrons, just like argon, again a low energy stable electron configuration. Note on the periodic table, chlorine is a nonmetal far to the right in its period. It is one electron away from argon, so it just needs to gain one electron to become like argon and get that low energy stable electron configuration. One more thing to note about electron affinity. Here is the chlorine atom. Here's the chlorine ion that has added the electron. It's a loss of energy that is called electron affinity. It's typically associated with a negative change in energy or a going to a lower energy state. And finally, in terms of definitions, electronegativity is the tendency of an atom to gain electrons when combining with another element. Looking at the four major forces that affect periodicity, that pattern of repeating properties on the periodic table, they are nuclear charge, shielding, electron repulsion, and electron configuration. First, nuclear charge. The greater the number of protons in the nucleus of an atom, the more positive it's going to be and the more strongly the electrons are held. It's important you understand that this is responsible for all period trends. And if we look at, say, period 3, we can see that the atomic number increases across, going from 11 protons to 12 protons, all the way up to 18 protons. So as the number of protons increases, the positive charge on the nucleus increases, and that causes these three things we just defined all to increase. Because of the greater positive charge, it makes it harder to remove the outermost electron, making the first ionization energy increase. It makes the electron drop more in energy level or energy, and therefore that causes the electron affinity to increase, that greater negative change in energy, and elements are more likely to gain electrons when combining with other elements because of that increased positive pull on the nucleus. Note that the nuclear charge also increases down a group, but we say it is not responsible for group trends, only responsible for period trends because of shielding. And shielding is the inner energy levels tend to reduce the nucleus's attraction for electrons in the outer energy levels, and this is responsible for group trends. So as we go down a particular group, we can see that the energy levels increase. The first period has only one, second is two, third is three, fourth is four, fifth is five, and so on. And it's important to note that if you go across any period, the shielding, the number of energy levels does not change, which is why it is not responsible for period trends, but only responsible for group trends. And because of that increased energy levels as you go down a group, that blocks out that nuclear charge, which again is why we don't use nuclear charge for group trends, but only for period trends. That addition of energy levels down a group blocks out the nuclear charge. And so if you can imagine an electron in the outer energy levels of each of these atoms, because they're further from the nucleus, because there's more energy levels in between that outermost electron and the nucleus, it causes all of these things to decrease. It makes it easier to remove the outermost electron. It makes a less of a negative change in energy when an electron is added to it, and it makes it less likely to gain electrons when combining with another element, and so those things all reduce. So summarize the periodic trends in first ionization energy, electron affinity, and electronegativity. All these things increase across periods because of nuclear charge. All these things decrease down groups because of shielding. And so if we were to compare sodium and potassium, the sodium is going to have a greater first ionization energy, greater electron affinity, greater electronegativity, because potassium is going to have more shielding, which blocks out the nuclear charge, which makes all those things decrease. If we were to compare sodium and magnesium, magnesium would have the larger first ionization energy, electron affinity, electronegativity because of nuclear charge. Sodium has 11 protons, magnesium has 12 protons. Because of that greater nuclear charge, it makes it harder to move the outermost electron. A greater change when you add an electron to it, a greater loss of energy, and it makes it more likely to gain electrons when combining with another element. The trend on the other side would be exactly the same. If we compare sulfur and chlorine, chlorine would be greater in all of those things because of nuclear charge. If we were to compare chlorine and bromine, chlorine would be greater than bromine because of shielding. Bromine has one more energy level than chlorine, making it reduce the pull from the nucleus, making all those things decrease. If we look at first ionization energies, here's the first period. Again, we see an increase across the period. Here's the second period. Again, we see an increase across the period. Here's the third period. We see an increase across the period. But note, we have a couple little changes here. Boron is less than beryllium, and oxygen is less than nitrogen, and that can be explained by the third force, which is electron repulsion. If we look at nitrogen, and we're talking about first ionization energy, the energy needed to remove the outermost electron, here is nitrogen's outermost electron. Here is oxygen's outermost electron. It's actually easier to move oxygen's outermost electron because of electron repulsion. Here we have two electrons in the same orbital. That is going to create repulsion, and because of that repulsion, it's actually easier to remove the outer electron of oxygen, making a decrease as you go from left to right, a change in the periodic trend. And between beryllium and boron, here is beryllium's electron configuration. Its outermost electron is in the 2s, whereas boron's outermost electron is in the 2p. Since the 2p is further away from the nucleus, it's a more outer energy orbital, it is actually easier to move that outer electron, again showing a decrease in the ionization energy rather than an increase across that period. So there are some exceptions which typically are due to electron repulsion. In the case of beryllium and boron, it's just that boron's outermost electron is further from the nucleus of the atom. Electron affinity, again, we can see a change in a trend. Again, we need to think of electron affinity as the greater negative change. And so here is lithium, beryllium, boron, carbon, nitrogen, oxygen. Here basically is the second period of the periodic table. And there's a lot of change in electron affinity. But again, we see a greater loss of energy going to a more negative change, indicates a greater electron affinity as you go across the period. But let's look at carbon and nitrogen. Now we have a more positive change in electron affinity, which would be considered a decrease in electron affinity. Why does it Why is it less of a loss of energy to add an electron to nitrogen than it is to carbon? Remember, electron affinity is the energy change associated with adding an electron. It's a loss of energy, and so nitrogen has less of a loss of energy. It's actually an addition of energy when you add an electron. And again, it goes to the idea of electron repulsion. Here is carbon's ground state electron configuration. If we want to add an electron to that, carbon has this open orbital that you can put an electron in, and that creates a fairly stable 3 unpaired electrons, half filling the 2px, 2py, 2pz. If we add an electron to nitrogen, now we're adding it to an orbital that already has an electron. That creates electron repulsion. Electron repulsion is going to be unstable or unstable. That means a higher energy. And so by adding that electron, you're creating instability and therefore at a higher energy level. And again, lower energy means more stable. Electron configuration is probably the most important key organizing factor of the periodic table. We have these big gaps in the periodic table because it's arranged so that all those in the first period end in S1, all those in the second period end in S2, and then here's the P block. All these are P1, P2, P3, P4, P5, P6. Helium also ends in S2. And because all these things have the outermost electron configuration in the same group, then members of the same group are similar to each other. And so we can identify these different groups as the alkali metals in group 1, except for hydrogen, alkali earth metals, and so on across the periodic table, but that's another story. But here we have the blocks of the periodic table: S block, P block, D block, F block. The S block has the S orbitals being filled. P block has the P orbitals being filled. D block is 10 wide because 10 electrons can go into the D orbitals and so on. The F block is down below. That leads us to the periodic law. When the elements are arranged in order of increasing atomic number, you will see a periodic pattern in their physical and chemical properties. And again, periods are the horizontal rows. So if I pick a particular period, say the 4th period, potassium is an alkali metal. Calcium is an alkaline earth element. Scandium to zinc are the transition metals. Gallium is another kind of metal. Then we have metalloids in germanium and arsenic. Then selenium is a nonmetal. Bromine is a halogen. Krypton is a noble gas. If we go across period 5, we see the exact same pattern. Alkali metal and rubidium, alkaline earth metal and strontium. Then we have 10 transition metals. Then we have other metals in indium and tin. Then we have some metalloids. Iodine is a halogen. Xenon is a noble gas. So again, the periodic law, we see patterns across periods because of the arrangement of the elements by order of increasing atomic number, but more importantly by electron configuration. Hope you learned a lot.